All right, let's talk about quantum mechanics. Now, the quantum mechanics that you need for general chemistry is not nearly as in depth as you could possibly get with quantum mechanics, but there are just a couple foundational concepts in quantum mechanics that we need to establish and talk about before we start talking about the structure of the atom and how electrons operate. So, in quantum mechanics, we think about things acting as waves. So, wave is an oscillation through a medium, simply put. You can have acoustic waves, you can have electric waves, magnetic waves, all kinds of different waves. But the important things are that, as you can see in the picture of the sine wave, you have the wavelength, which is the distance, basically one full cycle of the wave, up and down and back up. Or, start in the middle, down, up, end in the middle, or start at the bottom, up, down, end at the bottom. The distance from the center line to the peak or to the trough is called the amplitude. And then the number of waves that pass by you in a certain amount of time, that's the frequency. So if you were in a fixed point, you were watching a wave go by you, the number of wavelengths that pass you in a given second is the frequency. So wavelength is designated as the lowercase Greek letter lambda, and it's measured in meters. And frequency is the Greek letter nu. It looks like a V, depending on what font you're using. It might look like a curvy V, but it looks like a V. So the frequency is measured in 1 over seconds, which is all called hertz. So if you see Hz hertz, that's 1 over seconds, because again, it's how many pass per second. So it's how many waves per second. And the relationship between these two is the speed of light. So the speed of light in a vacuum is 3 times 10 to the 8th meters per second. And so the speed of light is equal to the frequency of a wave times the wavelength of a wave. Generally speaking, you're not solving for the speed of light, because the speed of light in a vacuum is constant, is considered a constant. So what you can do is, if you know the frequency, you can solve for the wavelength, and if you know the wavelength, you can solve for the frequency. For instance, what's the frequency of light with a wavelength of 700 nanometers? Well, if C equals nu times lambda, then lambda is C divided by nu. And nu is C divided by lambda. So in this case, nu is 3 times 10 to the 8th meters per second divided by 700 times 10 to the minus 9th, because it's nanometers. Meters cancels out, and you get 4.28 times 10 to the 14th 1 over seconds, or hertz. Hertz, the frequency is generally going to be very high. And as you see, that the frequency and the wavelength are inversely proportional, meaning as the frequency increases, the wavelength decreases. And then you can do it the other way. What is the wavelength of light with a frequency of 97 megahertz? So, for example, a radio station. I say light, the wavelength of electromagnetic radiation would be a better way to put it, but whatever. So lambda is C over nu. So lambda is equal to 3 times 10 to the 8th meters per second over the frequency, 97 times 10 to the 6th. So mega is 1 million, 10 to the 6th. 1 over seconds. 1 over seconds cancels, you get meters. So the wavelength for that instance would be 3.09 meters, which is a very long wavelength. So now that we've talked about waves and the relationship between frequency and wavelength, let's talk about electromagnetic radiation. So electromagnetic radiation is a wave that has two components, one electric, one magnetic. They're orthogonal to each other, meaning perpendicular. So like one's along the x-axis, one's along the y-axis is the way to think of it. And it's generally, when we're thinking about the transmission of energy, we're thinking about electromagnetic radiation. Now, like acoustic waves and seismic waves can carry energy too, but we're not really considering those when we're thinking about energy transfer. We're mostly thinking about electromagnetic radiation. It's by no means the only way, but it's the primary way that energy gets transferred. So it comes in discrete packets that are called either quanta or photons. So you've probably heard of photons. Basically, waves act like particles. We'll talk more about that a little bit later. But the spectrum that actually makes up visible light is this teeny tiny sliver. This teeny tiny sliver right here. So this little band right here, that's the stuff we can see. So it goes from about 900 nanometers to about 400 nanometers. That's the visible spectrum. Below that is infrared. Above that is ultraviolet. So infra under red, so it's lower frequency than red energy, red light, and then ultraviolet, ultra above, so it's above violet light. So X-rays and gamma rays and all those other things, those are the same stuff as visible light, but it's just much higher in frequency and lower in wavelength. Stuff like radar and FM radio and stuff like that, those are a much lower frequency and much longer wavelength. So the energy of a photon is going to be proportional to its frequency. So higher frequency means higher energy. And it's inversely proportional to the wavelength. So if we go back to this chart, right, as you move this way, we have lower wavelength, which means we have increased energy. As we move this way, we have increased wavelength, which means lower energy, right? So if the visible light spectrum, red is low energy, relatively speaking, and purple is high energy, relatively speaking. So X-rays are higher energy than that. Gamma rays are higher energy than that. So, when you think about like, oh, this radiation damages you, we're thinking about UV rays, X-rays, gamma rays. The reason these damage you is because they're very high energy, and so those very high energy waves can damage your DNA. Like that's what's going on there. So the ones that are down here, like microwave and things like that, don't have enough energy necessarily to directly damage your DNA or can't penetrate your skin. So that's kind of what's going on there. Now, don't get me wrong, microwave could still be dangerous, right? Because it can potentially heat up the water molecules in your body, which could be dangerous. But don't microwave yourself. Could be problematic. But again, the stuff we can actually perceive is this teeny tiny band. There are some people who have an extra rod or cone, which are the cells that we use to perceive light, and I believe that they can actually pick up stuff outside of the normal spectrum. And so there are also animals that can see outside of the normal spectrum. So there are biological creatures that have an expanded spectrum that they can look into, and some have a more limited spectrum, right? But for humans, generally speaking, 400 to 900 is the wavelength of light that we perceive. So back to energy of a photon. The equation uses something called Planck's constant. Maxwell Planck, he was a physicist. It's a lowercase h, and it's 6.636 times 10 to the minus 34 joules times seconds. It's a very, very small number because a photon, one singular photon, does not have a lot of energy. Obviously, you're getting bombarded with hundreds, thousands, millions, billions of photons, not protons, photons. There's a difference when you're observing light. So the relationship is that the energy is equal to Planck's constant times the frequency, which if we go back a few slides to the relationship between lambda and nu, we see that lambda or nu is equal to c over lambda. So we can substitute that in. Right, so we substitute c over lambda in for nu, and we get E is equal to hc over lambda. So if we know the frequency, we can find the energy. If we know the wavelength, we can find the energy because h and c are constants. And then if we know the energy, we can find either the frequency or the wavelength. So we could say, what is the energy of a photon with a wavelength of 450 nanometers? E is equal to hc over lambda. So you do 6.636 times 10 to the minus 34 joules times seconds, times 3 times 10 to the 8th meters per second, and you get, or divided by 450 times 10 to the minus 9th meters, and you get 4.424 times 10 to the minus 19th joules. For visible light, this is about, 10 to the minus 19 joules is about the right range, just so you have an idea of where you're shooting for. And we said, what's the energy of a photon with a frequency of 9.38 times 10 to the 15 hertz? E is equal to h times nu. So we just 6.636 times 10 to the minus 34 joules seconds times 9.38 times 10 to the 15th hertz. And you get 6.16 times 10 to the minus 18 joules. So this would be higher in energy than our previous photon, which means it would have a shorter wavelength. And we can solve for wavelength with energy as well. So let's say we have a photon that has an energy of 5.96 times 10 to the minus 19 joules. Well, E is equal to hc over lambda. So lambda is equal to hc over E. So we plug those numbers in, 6.636 times 10 to the minus 34, 3 times 10 to the 8th meters per second, divided by 5.96 times 10 to the minus 19 joules. And you get 3.34 times 10 to the minus 7 meters per second. Okay, so here are some problems for you to solve. What is the wavelength of a photon with a frequency of 90 gigahertz? So giga, capital G, is 10 to the 9th. So it's 90 times 10 to the 9th hertz. So remember that nu equals c over lambda. Lambda equals c over nu. E equals h nu equals hc over lambda. C is 3 times 10 to the 8th meters per second. And h is 6.636 times 10 to the minus 34 joules times seconds. So here we'd say, all right, well, lambda is equal to c over nu is equal to 3 times 10 to the 8th meters per second divided by 90 times 10 to the 9th hertz. You get 3.33 times 10 to the minus 3 meters. Okay, what is the frequency of a photon with a wavelength of 200 nanometers? So nu is equal to c over lambda, 3 times 10 to the 8th meters over seconds, divided by 200 times 10 to the minus 9th meters. And you get 1.5 times 10 to the 15 hertz. What's the energy of a photon with a wavelength of 1,000 nanometers? So E equals hc over lambda. So you plug all that in, and you find that it's equal to 1.99 times 10 to the minus 19 joules. What's the frequency of a photon with an energy of 2.03 times 10 to the minus 17 joules? Well, E equals h nu, so nu equals E over h. So it's 2.03 times 10 to the minus 17 divided by 6.636 times 10 to the minus 34. And you'll get 3.06 times 10 to the 16th hertz.